All right, well, I guess we just as well get started. And our meeting is going, but I don't think we got anybody joining us remotely. So, okay, last time we were talking about generating molecular orbitals for ethane based on group orbitals for pyramidal methyl that we had derived. And we had gotten to the point where we mixed the two lower energy sigma methyl groups together to give us the in phase and the out of phase combination. There's not a huge amount of splitting here upon mixing. That is, by that I mean we're the bonding orbital and the anti-bonding orbital. There's not a huge energy difference between the two because there's not a huge amount of overlap between these two S type orbitals on the carbons. Next, but these orbitals overall are lower in energy because they have all S character. We move up to the pi type orbitals, group orbitals for methyl that we talked about last time. This one is in, you have the P, I think we said X, 2px orbital with in phase with an S orbital here, and then two 1s orbitals down there. And then the 2py orbital in coming out and then back in the page. No orbital density on this proton. The appropriate phase relationships is indicated there. We bring them together and we get sort of pi type overlap here, the yellow phase and the pink phase above and below. I believe what we've called the YZ plane. In contrast, over here on the right, we have, oops, that's not actually even kind of correct. The node is the plane of the page. In front of the page, it's pink, and in the back, it's yellow. Sorry, Isabella, go ahead.
So we know that ethane usually doesn't like to be eclipsed, and
Uh-huh.
that's the way it's drawn here. So if you're going to mix the orbitals with the CH3 groups rotated so the hydrogens aren't eclipsed, does that change what can overlap?
That is a great question, and you've caught me. I didn't even think of that. I was just trying to make things fast and easy. So yeah, if we were to draw this in perhaps the most stable conformation, then we would do something like you've just described. We're going to see in the next chapter, and you maybe remember this from 351, that the barrier to rotation is about 3 kcals per mole. And at room temperature, you've got about 0.6 or 1, roughly 1 kcal per mole of thermal energy to deal with. And that's on average more than enough to allow for free rotation over that barrier. So we can definitely show it that way.
Okay, so even if it made the top like pi orbital not overlap as well, that would still be okay.
Well, yeah, though let me, dang it, let me show you what that would look like. Except I'm behind and I'm confused. All right. So that's a more realistic conformation, I think, is what you're saying. So let's just erase. Sometimes I want the eraser to be large. Sometimes I want it to be small. Why can't it just know what I want? All right. Oops. Okay. Now we're cooking with gas. All right, let's do the one, start with the pi orbital that's sort of on the left. And let's draw it in the staggered conformation. Yeah, we could still make everything overlap in phase. We just have to change how we color things. I'm sorry that this is sort of sloppy. Okay. Yeah, it kind of does make things more even. And I agree with you that that's more realistic. I suppose you could ask the question, well, what the heck happens to these orbitals upon rotation? How does everything stay in phase? And I don't know. I don't know how to answer that question, other than to suppose that the electrons aren't the same as the nuclei, so maybe the electrons don't have to move. Just sort of adjust their relative distributions. Yeah, so for the one where these hydrogens in the plane of the page are actually in the node, I guess we would draw the orbital like this, with pink in front and yellow in the back. And if we go look at Spartan and look at what the orbital for ethane looks like, they do actually draw this in the staggered conformation. All right. Okay, great questions. Others? We haven't dealt with the anti-bonding version of the pi orbitals. So if we were to do that, all we have to do is copy what we've already drawn. In terms of where they're going to show up, it's not a major issue for us. It's not something that you would necessarily need to predict. Qualitatively, you would know that these two pi orbitals are going to be higher in energy than the bonding orbitals were lower in energy. To make the pi orbitals, all we really have to do is get the phase right. Da, da, da. So this is the out of phase combination. Let's see. And you might be looking at this and saying, well, hold on. Why are we worrying about this? Isn't this an anti-bonding orbital? Turns out that we're going to have enough electrons to populate these sort of out of phase pi minus pi type orbitals. And notice, even though they have carbon-carbon anti-bonding character, they still nonetheless have substantial carbon-hydrogen bonding character. So overall, these are going to be bonding orbitals. And maybe I'll just illustrate that by sort of showing you what you would see if you were looking at Spartan for these molecules. You would see an in-phase lobe of electron density between the carbon and the hydrogens on one side of the molecule and the carbon and the hydrogens on the other side of the molecule. In fact, if we go to Spartan, what we've got here is actually going to look very much like a pi star for a pi bond. Only the lobes on either side will be between carbons and hydrogens and have substantial carbon-hydrogen bonding character. Okay, questions so far? The last one we're going to do is going to be combining the, the sigma out orbitals that we drew last time. I'm not sure how high up I should put them. We're not worried about absolute energy relationships. Remember that the sigma out orbitals involve sort of an sp3-ish kind of hybrid on the carbon and then 1s on the hydrogens. in phase behind, and then a lobe sticking out. This is the sigma out. And we've got the other one, same energy over here. And we can bring these together. And this is perhaps the one that resembles a bond most, because if you were to bring these two together, you've got substantial orbital overlap along the line between the two nuclei. And because of that large orbital overlap, the sigma out plus sigma out orbital, except Josh can't spell out, is going to be actually lower in energy than the out of phase pi CH3 combination. If you were to draw this combination, you would just bring the two orbitals together in phase, and maybe you would show a slightly fatter lobe there in the middle where the orbitals overlap. And this one is substantially carbon-hydrogen bonding and also strongly carbon-carbon bonding. All right, so that takes care of, let's see, in ethane we have 2, 4, 6, 8, 10, 12, 14, 7 pairs of electrons. And we've just generated 7 bonding orbitals. And so we can populate them with electrons. And now you have a clearer picture of what the electrons in ethane are doing. Those of you that took my 351 class recall that we used to draw sort of energy diagrams for things with lots of carbon-hydrogen bonds, and we basically said there was a non-bonding line here, and we had all of the carbon-hydrogen and carbon-carbon sigma bonds there, and all of the carbon-carbon and carbon-hydrogen sigma stars up there. They're not all equal in energy, and so now you know why. Okay, so that is our picture of bonding in ethane. I haven't showed you any of the anti-bonding combinations. We will do some of those when they become relevant for us, but we're not going to use ethane as an electrophile, so there you go. Questions? Should we go to Spartan and confirm that we've got this right? So that's the sigma plus sigma, sigma minus sigma, pi plus pi, another pi plus pi. This is the sigma out plus sigma out. You've got carbon-hydrogen bonding character here in the blue, and carbon-carbon bonding character there. And this is the one that most closely represents our previous concept of bonding. Then the highest energy electrons are in this degenerate pair of pi minus pi combinations, which are carbon-carbon anti-bonding, but which maintain carbon-hydrogen bonding character. All right. So, of course, we're interested in more stuff than just ethane. So let's do an alkyl halide, shall we? So what we're going to do is take these 6 or these 4 orbitals from the methyl group, and we're going to erase the extraneous lines. And then let me drag them down here. And then let's say we want to do methyl chloride. Okay. Now you can go in your text and you can look up electronegativities of or orbital energies for carbon versus chlorine. And what you would find is that the chlorine p orbitals, even though they are from a different row of the periodic table, the chlorine p orbitals are nonetheless still lower in energy than, say, carbon p orbitals. So if you recall from when we were making these methyl group orbitals, the sigma out orbital is substantially lower in energy than the carbon 2p, x, y, and z. We're going to put the chlorine px, py, and pz here. And we're going to say this is, I forget what our coordinate system was. Is this z, this is x, and this is y? All right. And then there would be a chlorine s orbital. And I'm not sure actually what the math tells, what the data say for the relative energies of the carbon versus the chlorine s orbital. It's going to turn out not to matter to us too much because those are going to be orbitals that are already filled. Go ahead.
So the S there is a 3S, not a 4.
Yeah, this would be, well, whatever chlorine is. I forget what row. Yeah.
It's row 3, but 4S.
There it is.
The 4S starts to fill with potassium, so it won't be that much further down.
Yeah, it'll be the 3S for chlorine. And again, if you find out that it's actually not this way, then hopefully you can forgive me. If I had my text here, we could look it up. Does anybody have their book? No, that's okay. You don't have to bring your book to class. That's silly. I used to lug my books to class when I was all through my undergrad career, and it was a waste of time. So anyway, all right. So the 3s orbital on chlorine is going to just look like a s kind of orbital. So because these two orbitals are not the same in energy, we're going to make a bonding one and an anti-bonding one, but we're going to say that the bonding one is going to more closely resemble chlorine than it does the methyl group, whereas the anti-bonding one should more closely resemble carbon versus chlorine because it's closer in energy. So what would this look like? So for chlorine, we'll draw an s orbital there, and we'll have more of, that's not what I wanted to do. We'll show a bit more, not a huge amount more, but a bit more of this on chlorine than it is on carbon. And then for the out of bonding arrangement, the sort of minus combination, we'll draw it with more of that higher energy orbital on carbon than on chlorine. It's very subtle. All right. What are we going to do with the pi orbitals? Well, a question you could ask is, can we line up this pi CH3 orbital with one of the p orbitals from chlorine? Shouldn't be a huge deal, right? Should be pretty straightforward. Okay. And again, I am not sure what I know that the p orbitals from chlorine are lower in energy than the sigma out orbital. I'm not sure about their relationship with, their relative relationship with these pi type orbitals. So we won't make a big deal out of that. We'll assume they're fairly close in energy. Sure, if we took this particular pi CH3 orbital, we could use the corresponding, let's see our coordinate system, I guess the px orbital on chlorine. And we could generate that in phase combination. And similarly, we could take the other, same in energy, pi CH3, and mix that with the py orbital on chlorine. Again, because I'm not confident in the relative energies of these pi CH3 orbitals and the chlorine p orbitals, I'm not making a big deal out of the orbital coefficients and which is bigger where. Okay. And then of course we would have the corresponding out of phase combinations, which we could put here. And I suppose we could draw them, why not? Only we need to change the phase colors. To have an out of phase relationship. Okay. What about overlap between sigma out and the 2pz, or I'm sorry, the 3pz of chlorine? That's going to be closer in energy, of course, to chlorine than it is to the sigma out orbital. By how much, who knows? We could figure out the numbers. It won't matter for our discussion, which is going to be purely qualitative. We would expect that bonding orbital to be, as I mentioned, more on chlorine than it is on carbon. So we could draw something, oops, maybe I want to use gray there. A lobe here, and another lobe there. A smaller lobe there. And I don't know how fat or large that lobe on the back of chlorine needs to be in order to be realistic, but we just want to communicate that more of this in-phase combination should be on chlorine than it is on carbon, because the chlorine orbital is lower in energy. And then we would draw the out of phase combination. And this is going to be closer in energy to our starting sigma out orbital than we saw in ethane. In ethane, we didn't draw this anti-bonding combination because it wasn't relevant. It was very high in energy. Because of the initial gap in energy between sigma out and chloride, this anti-bonding orbital is not going to be that much higher in energy than sigma out. And so we can actually draw what that anti-bonding orbital will look like. And what our qualitative molecular orbital theory rules tell us that more of that out of phase combination should be on carbon and less on chlorine. So we might draw that, oops, this way. And this starts to look like what you maybe have drawn previously for what a sigma star looks like. There's a large lobe on the backside of carbon. there are smaller lobes in between and a smaller lobe on the outside of chlorine. Okay, so now we can fill this. Well, let me just pause. You see how we generated all of that? The only difference between that and ethane is we were dealing with a smaller set of orbitals from chlorine. Well, no, we were still dealing with 4 from chlorine, only we had a 3s and 2 and 3 degenerate p orbitals. We were also dealing with this energy difference where the chlorine p orbitals are lower in energy than our sigma out. That has the consequence of the bonding orbital being here mostly on chlorine and the anti-bonding orbital here being mostly on carbon. Now let's figure out how many electrons we've got to deal with. There's 2, 4, 6, 8 plus 3 lone pairs on the chlorine, so 14. Yes, sort of. You get that right? So let's fill them up. 6, 8, 10, 12, 14. We've got the HOMO here and the LUMO here. Couple of interesting conclusions that change the way we've maybe thought about alkyl halides before. Are all of the non-bonding lone pairs actually non-bonding? And are they all the same? Are they all equal in energy? They're not equal in energy. You have 2 of them that are, and you have 1 of them that's lower in energy. Okay, so chlorine in our alkyl halide is going to have 3 lone pairs, though they're not in our MO picture, they're not exactly lone pairs. They are substantially carbon-chlorine bonding and carbon-hydrogen bonding. And then these 2 are substantial carbon-hydrogen bonding. So these are maybe more like the lone pairs that we're used to thinking about, mostly on chlorine with a little bit of carbon-hydrogen. Okay. Does that sort of make sense? The highest energy orbitals that we've thought of before in an alkyl halide, oh, that's just the lone pairs on the chlorine. Well, it's a little more complicated than that. Second, and in fact, as you look at it, it's kind of confusing because I'm in the MO picture, I'm not sure I can identify 3 lone pairs. You might think it's that one, and it sort of is, but this is also the one that's substantially carbon-chlorine bonding. So it would be weird to call that sort of lone pair or non-bonding. All right, and then the LUMO being the carbon chloride sigma star basically is a nice conclusion that comes out of our analysis that agrees with stuff that we would have done before. And this explains in large part why when a nucleophile comes to attack an alkyl halide, it's going to do so on the carbon because that's where most of the LUMO is. All right, anything you want to ask? Any comments, questions on methyl chloride? We could do the same thing. We could go over to Spartan and draw methyl chloride and just confirm that we've got, come on, erase. Just confirm that we've got the right sorts of things. All right. Here's that lowest energy orbital that's mostly on chlorine. Here's a higher energy one that's now mostly on carbon with the node in between. Here's one of the pi plus p orbitals. Here's the other pi plus p orbital. Looks like they're mostly on carbon. Here is the sigma out on carbon plus the 2p or the pz orbital on chlorine. Looks what we would expect for a sigma bond. Sorry, kind of moving all over the place. And we've got 2 degenerate lone pairs in our highest occupied molecular orbital, which are mostly on chlorine, but are substantial, but are also a little bit of carbon hydrogen bonding. We'd call these 2 our lone pair. And then our LUMO is the, how do I wrote, no, I'm not gonna, okay, I have to touch part of the molecule and drag it. This is our carbon chlorine sigma star, basically. All right. So we're getting pretty close to calculation, to values that, or to pictures that we get from calculations simply by mixing things together. All right. There's a ton of these we could do. They're in the text. Of particular interest is formaldehyde, because it gives us our first look at a carbonyl compound. We can go through that in the same way that we have here, or alternatively, I can just paste the picture and we can talk through it. But I understand that some of you have been working on some problems and maybe have some questions. So what issues are you facing? What things are confusing? Yeah.
So what are you supposed to do for this if you don't know exactly what the geometry of the final molecule looks like? Because one of the book problems was do this for protein formaldehyde, and I'm not sure if the hydrogen is sticking straight out or if it's an angle.
Okay. Yeah, that is a good question. So what if if you're not exactly sure what the final geometry should be? Because your text does take you through what the orbitals for formaldehyde should be just by combining the group orbitals for bent CH2 with the atomic orbitals for oxygen. But what would you do if you wanted to bring in OH instead of oxygen? What are the relevant group orbitals there? I don't know, though I would think for something like OH, there is no geometry, it's just a line.
Yeah, but like the final molecule, is it like COH followed 180 degrees, or is the H like?
I don't know. Should we see? That's a good question. So let's just sort of hypothesize what the group orbitals would be for this OH group. You have an oxygen and you have a hydrogen. So probably you've got lowest energy overlap of a oxygen and hydrogen. You would have one for sure that would look kind of like this in phase. And then you'd have the out of phase combination as well. I'm not going to worry at this stage whether one is more on the hydrogen than it is on the carbon. We could figure that out, but what happened there? I don't think that'll be too important. And then what else? Well, I think you'd probably have the p orbital on oxygen overlapping with the s orbital on hydrogen. Oh, probably this would just engulf the hydrogen. And then I think you would be left with two degenerate p orbitals orthogonal to the one we use to make the oxygen-hydrogen bond. And I'm just spitballing here because I haven't looked at the answer to that problem. Does that look sort of reasonable? Yeah, Michael, did you have you raising your hand? No?
No.
Okay. I'm trying to think about number of electrons we've got. I don't think we need to worry about that because we construct the orbitals first and then we and then we worry about the electrons. So over here, yeah.
One question we did have at this stage was, normally when we're telling like relative energies of orbitals, we just look at number of nodes, but obviously we have 4 orbitals that all have 1 node. How do we order them properly in terms of low to high energy?
On oxygen,
Yeah, for those 4
for that OH group.
Because for the diagram, obviously we're going to need to have them in the proper order of energies.
Yeah. As I look at this, my guess is this is anti-bonding. And this is in contrast to what we've done before with group orbitals like methyl overlapping. Remember, we even in the anti-bonding combination, we still had substantial carbon-hydrogen bonding character. That's not the case for the sort of 2s minus 1s combination. So my guess is this is high and empty. So my guess is the ones we're going to worry about for making bonds are these 4.
And so we have the 2s plus 1s, and we have the 2p plus
My guess is,
1s.
yeah, this is lowest because you've got S character. This is next because it's bonding, and then these are, yeah. Okay. So now that we've got our alphabet, we should remind ourselves of what the group orbitals on CH2 are for bent CH2. You have the one that looks like this. I guess I need to be less sloppy with my drawings. So you have the sort of all in phase option. You have the pi type option. And then you've got the sigma out kind of option. And then lastly, you would have the leftover p orbital. Sorry. And then let's see, that p orbital that we have would be the one that is coming out of the page at us, I think, based on how we've drawn things. Is that okay? So now we're just going to stitch them together in the best way that we think possible. Yeah.
Something else that we were wondering is, it seems like every time we do molecular orbital diagrams, again, we like order the orbitals from like lowest to highest, and then you just combine the 2 lowest, the next 2 lowest, and the next 2 lowest, and the next 2 lowest, right?
Yeah.
Okay.
Well, so how do you know which ones to combine with which when
Yeah.
you're combining group orbitals? I think that's a really great question. I think it can be difficult to see, and I think you do it in the way that produces the best overlap.
Okay.
In other words, I would not choose to combine sigma type orbitals on one side with pi type orbitals on the other,
Right.
because sigma type orbitals are going to give me end-to-end overlap, which is going to be better than side-to-side overlap.
Gotcha. Yeah, that was a question we ran into, because on our OH molecule, right, that P plus S orbital, the second
Yeah.
one, like that's our second orbital up, right?
Yeah.
But if we order the CH2 molecular orbitals, the one that's like the next one in energy is a pi type orbital.
Right. So you're asking, should I do this? And the answer is no.
Okay.
Yeah, you want to, and so you're right that you want to look at combining orbitals that have similar energies, but a bigger issue is that they have the right symmetry. Yep. Okay, sorry. So now let's start putting them together. This is our lowest energy orbital from CH2, and then if we were to move this one over, except I didn't want the star to come with us. All right, that maybe looks okay. We're gonna see, because all we're gonna do here is draw the orbitals in this linear way, and then we're gonna ask, how does it change if I switch it? Shoot, okay. Then how about this? I probably want to combine that one with the corresponding p orbital on oxygen. In phase. In this case, the hydrogen would be in the node, so there wouldn't be anything there. Probably next, I would want to combine the sigma out among my remaining options, probably the sigma out with the sigma type orbital between oxygen and hydrogen. I would need to do it in phase. And I suppose it would look like this. And then lastly, I would combine P with the other p orbital on oxygen that has the right symmetry. Okay. And then there would be anti-bonding combinations as well. But let's see what we've got so far. How many electrons do we have in protonated formaldehyde? This will tell us whether we need to populate any out of phase combinations. 2, 4, 6, 8, 10. We've made 5 orbitals. I'm sorry, 4. So what's the next one we need to do? I'm not sure whether it should be the out of phase combination here or instead the out of phase combination there. I don't know. Yeah.
Also, wouldn't we like order them differently? Just like the one that has 3 nodes, shouldn't that be higher than the other one that has 2?
This one has 2 nodes. These
2 versus 1.
2 versus 1. I'm not sure that works. It certainly works when comparing orbitals of like the same symmetry, pi versus pi star. I don't know that it works as well when comparing pi versus sigma, because pi orbitals keep the electrons further away from the nucleus than sigma orbitals do. So it may be that you can't necessarily make that comparison.
Just kind of don't know how to order them.
Right. So there are some other out of phase combinations we might have dealt with too. The out of phase combination for the first would look like this. And based on analogy with what we've done previously, it may be that those are our 5 orbitals. So it may be that this is 1, this is 2, then 3, then 4, then 5. I'm not sure, but that may be sort of what you're looking at. Yeah. Shouldn't 3 be degenerate with 5? 3 will probably be lower in 5 because of the extra carbon hydrogen bonding character. Does that take care of all 5 electrons? I'm five pairs, or do we have more than that? 2, 4, 6, 8, 10, 12. We have 6. Okay, in that case, we've got to deal with the out of phase version of this. All right, so in case we're confused by all of this, we're gonna label things so that we can tell where each of these orbitals came from. We haven't drawn a nice diagram here, and oh well. Sucks to be us. All right, so orbital 1 is basically a sigma plus sigma type orbital. Orbital 2 is the sigma minus sigma type orbital. Orbital 3 is a pi plus p combination. I'm worried about relative energy levels, so let's deal with that in just a second. This is the sigma out plus p combination. This is a p plus p combination, and this is a pi minus p combination. So I'm pretty confident that in order of energy, 1 and 2 are our lowest energy. Based on analogy to what we've done previously, I think the pi type orbital, the pi plus pi, is probably next. My gut says that the sigma bonding orbital comes next, then the pi minus p, and then the p plus p. No? Should we see how it was in formaldehyde? All right, in formaldehyde, the order is sigma plus sigma, sigma minus sigma. You have the pi plus p, then the sigma plus p. Then in formaldehyde, the pi orbital is the pi bond, the p plus p combination is next. And then finally 6 is the pi minus p combination. Yeah. I will copy over just for comparison so you can see the results for formaldehyde and where they come from. Yikes. All right, with formaldehyde, oxygen orbitals are lower in energy than the carbon orbitals. So same sorts of arguments as we had last time with methyl chloride. These two lowest energy, sigma plus S and sigma minus S, should look pretty familiar. Here is the pi on carbon plus P. The carbon pi is lower than the oxygen P, so it's mostly on carbon. You've got overlap of the sigma out with a P from oxygen, again, mostly on carbon. Then you have P plus P overlap as a sort of bonding orbital, but the oxygens are lower in energy, so the pi bond is mostly on the oxygen. And then your highest energy orbital is the pi minus P combination. So I don't think adding the oxygen changes any of that. It just introduces the oxygen. So our question, I guess, that we could ask is, what would happen if we took these combinations and moved that oxygen out of the plane? I'm sorry, remove that hydrogen out of the plane. Okay, so Here, I don't see a huge problem if we did that. There's not a big change in overlap, so I don't really predict that that's much of an issue. If we did that here, oops, we could, that might actually be even more favorable, because whereas that hydrogen used to be at a node, now it could actually overlap in phase with the p orbital on oxygen. So that's probably lower in energy. Similarly here, that might decrease the extent of overlap between the lobe on oxygen versus the one on hydrogen. So maybe that gets a little higher in energy. Doesn't matter at all for the pi bond. So this one may be a little higher. Doesn't matter for the pi bond. Shouldn't matter for our sigma minus S combination. And then probably if we move this one up like that, probably again, we can take advantage of a bonding kind of interaction. So 6 probably goes down in energy, 4 maybe goes a little bit higher, 3 probably also goes down in energy. The others don't change. My guess is I'm pretty convinced that it should be up instead of pointing straight out. We can do some calculations. So now I will go up to my office and I'll do some calculations and I'll show you the results next time, and we'll see whether we're actually getting the right answer. How's that? Okay, kind of fun. Cool, good questions. We'll see you next time.